We're practically swimming in a sea of data these days, and we're always trying to find patterns, right? To make sense of it all, how does one thing actually affect another? Well, that is the big question we are tackling today, and we're going to use a really powerful tool called correlation to do it. Let's jump in.
I mean, think about it. You ask yourself these kinds of questions all the time, probably without even realizing it. Does spending more time at the gym really lead to weight loss? If I cram for 1 more hour, is my grade actually going to go up? We have these hunches, these gut feelings about how things are connected, but how can we ever be sure they're actually real?
And that's where statistics comes in. It's this incredible toolkit that lets us move past just, a hunch. It gives us a solid, objective way to measure these relationships and, this is the important part, to figure out just how strong those connections truly are.
All right, so let's start with the absolute basics. What exactly is correlation?
At its core, correlation is a statistical method for figuring out two key things about a relationship. First, the degree, which just means how strong is the connection. And second, the type. What kind of relationship are we even looking at? We're going to break down both of those.
So before you can measure anything, you've got to see it, right? And the go-to tool for that is something called a scatter diagram. It's simple, really. You just plot your pairs of data, like a person's height and their weight, as little dots on a graph. And the way those dots cluster together, or scatter, well, that gives us our first huge clue about the relationship. And when you look at that scatter diagram, you're usually looking for one of three main patterns. First is a direct or positive correlation. That's when the dots trend upwards, kind of like they're climbing a hill. As one thing goes up, the other tends to go up too. Think height and weight. Then you've got the opposite, an inverse or negative correlation, where the points trend downwards. And finally, you might just see a random cloud of dots. That's no correlation. There's just no clear pattern at all.
Okay, so seeing a pattern is one thing, but statistics is all about being precise. So how do we put an actual, concrete number on that connection?
We do it with something called the correlation coefficient, which we just call R. And the absolute beauty of R is how simple it is. It's always a number that falls somewhere between -1 and +1. That one little number tells you everything you need to know about both the strength and the direction of the relationship.
Let's look at this scale. A value of +1 means you have a perfect direct correlation. Imagine all the dots on your scatter diagram forming a perfect straight line heading up. A value of -1 is a perfect inverse correlation, a perfect straight line heading down. And a value of 0? That means there is absolutely no straight line relationship whatsoever. Now, most stuff in the real world falls somewhere in between, and the closer that number gets to 1 or -1, the stronger the relationship is.
So you might be wondering, how do we actually get that number R? Well, it's not a one-size-fits-all deal. Statisticians have a couple of different tools in their toolbox, and they pick the right one for the job based on the kind of data they're looking at.
And here are the two heavy hitters, Pearson versus Spearman. Pearson's method is your workhorse for quantitative numerical data, stuff you can actually measure, like height in centimeters or weight in kilograms. Spearman's rank method, though, is designed for something different. It's for descriptive data, or stuff you can rank in an order. Think about student grades like pass, good, and excellent. You can't put a hard number on good, but you definitely know it ranks higher than pass.
Okay, whoa, don't let this formula scare you. We are not going to do the math here, I promise. But this is Pearson's method. It looks super complex, but the idea behind it is pretty straightforward. It's just a very, very precise way to measure how consistently two sets of numbers move up or down together.
Now, Spearman's method, it's a little different, and honestly, it's pretty smart. Instead of using the raw values, it just ranks everything first. So for one variable, excellent becomes rank 1, good is rank 2, and it does the same for the other variable. Then it just looks at how closely those two sets of ranks match up. Clever, right? All right, we've learned how to find correlations and even how to measure them. But now we've reached what is, without a doubt, the single most important warning in all of statistics. Seriously, if you remember only one thing from this whole explainer, please make it this. This quote from our source material says it all. The relation does not refer to causation because it does not refer to the existence of an effect of a variable on the other. Let's say it one more time, nice and loud. Correlation is not causation. It is such an easy trap to fall into. Our brains are literally wired to see a pattern and assume there's a cause. You see a strong link between A and B,
Let's say ice cream sales and shark attacks both go up in the summer. It's so tempting to think one causes the other, but the real story is often more complex. There's a hidden third factor, C, in this case, hot weather. That's the real cause. It makes more people buy ice cream and makes more people go swimming.
Here's another, more serious example. We see a strong correlation between rising sea levels and rising global temperatures, but it's not as simple as one just directly causing the other. There's a much bigger, much more complex system behind it all, climate change, that is the underlying driver that's influencing both of these trends.
So with that huge warning ringing in our ears, let's pull all this together. What's the practical, real-world takeaway for you? All right, here are the 4 big things to lock in. 1, correlation is your go-to tool for measuring the strength and direction of a relationship. 2, the coefficient R tells you the whole story on that simple scale from -1 to +1. 3, you've got different tools for different jobs. Pearson for numbers, Spearman for ranks. And number 4, the most important one, always, always, always remember that correlation does not mean one thing causes another.
So I'm going to leave you with this final thought. The next time you're scrolling and you see a headline or a study that links 2 things together claiming some big, dramatic connection, what's the very first question you should ask yourself? Is this really causation? Or could there be a hidden story, a third factor that we're just not seeing?